Okay, so we've talked about the three different potential ways of looking at a logistic regression model, either on the log odds scale, the odds scale, or the probability scale. So rather than talking so abstractly, let's look at an example. So we're going to look at our sleep data again. These are the data where we have teenagers between the ages of, I believe, 14 and 18. And we ask them if they if they generally get at least 7 hours of sleep a night. And these data are on Moodle, and we'll take a look at those shortly. As a matter of fact, let me bring that up now. We can look at that now. So the sleep data are here on Moodle under the data sets. And I have them as both an Excel file and in this Moodle book. So here are the sleep data, and I have them both. And there's two pages in this book. There's the raw data and the counts data. So let me explain what that means. Okay. There's really two ways that you can enter data into SAS for logistic regression models. We can use the raw data, which essentially means that we have one record per observation, or we have one row again per observation. There are 446 observations in this data set. Now, just to remind you of something, I've taken a bit of a shortcut here in SAS, and to remind you of notation that you've seen sometime in the past. If you use this @ symbol, this means that there's actually multiple, this tells SAS that there are multiple data records on each line. So SAS will continue reading across the line. I could have listed these out down the page, but that would be a very long page because there are n equals 446 observations. So that's why I use the @ here. And I did that as well on the Moodle page. If you look at the raw data, here are the 446 observations. You can see, so that's why I used the @ so it didn't have to go way down the page. So each observation, this is for each student in the data set, we have just their age and whether they said they get 7 hours of sleep or not. So you can see that the first student that we have in the data set was age 14, and they said no, they don't get 7 hours of sleep. And we have, if we look back at our previous sets of notes, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 of those students who said no, who were 14 years old and said no, they did not get 7 hours of sleep. And similarly, after those 12, then the next 34 actually said that they were 14 and that yes, they do get 7 hours of sleep. So this is entering the data as the raw data. This is the way you typically have seen data in this class. But there's actually a more convenient way to enter data, or a more concise way to enter data for logistic regression. And we can enter the data exactly as we saw in the notes in Chapter 9a. Sorry, I had just paused my video because I realized I didn't have my Chapter 9a notes with me. So I wanted to make sure to get those. But I'm going to enter the data using summary statistics from the table in 9a. So here's the original table that shows our data. So remember we had ages 14 through 18. So the first column, there were 12 students who said no, they did not get at least 7 hours of sleep, who were also age 14. And 34 said yes. So we can enter the data exactly as we have them in this table because we don't actually need all the individual students listed out. We know how many of each were in each category. And so we can provide summary statistics data. So I'm going to enter data sleep, input age 7 hours again, the same two variables. I need to know how old they were and whether or not they got 7 hours of sleep on average. But now I'm going to also include this count variable that just tells me how many fall into each category. Again, I'm still going to use the at notation because I'm going to include the records from line to line, or across each line. So for this first cell, there were 12 students who were 14 years old and said no, they did not get at least 7 hours of sleep. So here, we enter those 12 students right here in our data set. So they're age 14, no, they did not get 7 hours of sleep, and the count is 12. Similarly, there were 34 students who were age 14 and said yes. So you can go across here and verify for yourself that these data, the way I've entered them here, are exactly the same as this table, as the grayed out section of this table. Okay. So that's a more concise, more convenient way to enter data for logistic regression. And if we're going to use the summary stats in logistic regression, we have to tell SAS that we're doing that. So proc logistic is our new procedure for doing logistic regression. Okay, so this is for logistic regression, and it functions very much the same way that we saw proc GLM and proc reg function. It's probably a little bit more like proc GLM than proc reg, so that might be good. If we're going to use the summary statistics approach, so if we're going to use the approach where we enter the summary statistics in our table, we have to tell proc logistic that we're doing that. So this freak count says we're using summary stats here. We're using the counts. And this is the variable, this is our variable name that we've defined, counts. Okay. Let me just say that. That's our variable name. That's in our data set. We're going to model our response variable now is 7 hours. So this is a little different than we saw in linear regression. Our variable now takes on the values either no or yes. It's a text variable. It doesn't have to be a text variable for logistic regression, but it can be a text variable. It can also be a 0-1 variable, or it can take on any numbers, actually. And I'm going to define here, I'm going to say that I want to model events equals yes. So I want to model in my logistic regression the probability that a student said yes, they get at least 7 hours of sleep. So this tells SAS what level of your response to model. And as you'll see later, it doesn't matter, it actually doesn't matter if we do this. You could equally model the probability that event equals no, or that 7 hours equals no in this case. You would actually get an equivalent model. You just have to you have to understand what level of the event or what level of the response you're actually modeling. So we'll see this a little bit down below. And then age, of course, we have only one X variable because we're doing simple logistic regression now. So as you'll see, proc logistic produces a lot of output. We'll discuss parts of it, but we won't discuss all of it. But here's a portion that includes our parameter estimates. And I'm actually going to go ahead and do this in SAS because I think it's worthwhile. So I'm going to go, so I could copy my raw data, but I'm going to go ahead and use the counts data version of the sleep data. And plug those into SAS. So I called this sleep 2 since I'm using the counts data. and I'm going to say proc logistic data equals sleep 2. And I want to show you something first. Model 7 hours, event equals yes. And again, when you put something in quotes, we have to make sure it is case sensitive, so we have to make sure that the capitalization and everything is the same as it is actually in your data set. Equals age, run. And I'm doing this. This is the incorrect way to do this. I just wanted to show you something. It will still run if I do this. Okay, takes a little while to run. Sorry about that. So it will still run. And notice that it tells me that there are 10 observations. Why are there 10 observations here? And that there are 5 no's and 5 yeses. SAS is only counting 10 observations here because I didn't tell it to use my counts, my cell counts. So it's looking at my table. It's looking at the data table again, and I didn't tell it to use the cell counts here. So it's saying that there are 1, 2, 3, 4, 5 times 2, 10 observations. So that's actually going to give me the wrong answer. If I'm using summary statistics, I have to make sure that I use freak count here, or freak count. And it doesn't have to be count. Count is the name of my variable in my data set that actually has the counts. But you might have a different name. So actually now I'm going to run this again. And now see what we get. So now it tells me that I have 446 observations, just like I was expecting. And here's the breakdown of the no's and the yeses. So you can see it gives a lot of output. We'll talk about some of this throughout this course. But the most important bit that we're going to talk about here first is the analysis of maximum likelihood estimates. Again, this is your table of parameter estimates, and we'll talk more about what this maximum likelihood means as we go forward. So now we're focusing on the parameter estimates, just like we did in simple linear regression. So here is our table of parameter estimates, and just like we did for simple linear regression, we can call this B0 or we can call this beta 0 hat. This is my estimated intercept, B1 or beta 1 hat. This is my estimated slope on age. Okay. This output should look very similar to what we would get in simple linear regression. Note that we do not have t statistics anymore. We actually have chi-squared statistics, and we'll talk more about that below. And then we have p-values associated with those. We'll come back to that. So here's a picture of our model. Remember what we saw in chapter 9a notes. We thought about possibly fitting this simple linear regression model to this data set, and it seemed to do okay within the range of the data, but the linear model had some characteristics that we didn't particularly like, in that, namely, it went beyond the range of probabilities. It went beyond 0 and 1. Well, now, if we fit this logistic regression model, this is the predicted model. So again, within the range of the observations, they fall right along the model, which is almost a straight line in that range. But now notice that we have that nice S-curve that tops out at 1 and bottoms out at 0. So, and this is the type of thing I'm going to ask you throughout this course. What's the equation now in terms of log odds? So remember that log odds, what I'm asking here is the log of p hat of x. Since we're dealing with sample data, we can use p hat instead of p. 1 minus p hat of x. We can also write that as logit p hat of x. And that's our estimate for beta 0 is 3.1186, and our estimate for beta 1 hat, is negative 0.1514 times age. So this is the estimated model, the equation, in terms of log odds. And that's what we get directly from Proclogistic. Now, note that the slope on age is negative, which is what we're seeing here. We have a negative S-curve as age increases. So what does success y equals 1 mean in this model? Remember what y equals 1 means. It means student does get, or at least says they get, at least 7 hours of sleep on average. So now let's interpret the model parameters in each of these different forms that we talked about. On the log odds model, we don't really have to bother to interpret the model parameters. The interpretation isn't really useful because we don't really know what log odds are. They're difficult to think about. Odds are difficult to think about, right? Beyond the idea of, is there evidence of a relationship or no relationship? Because if there's a relationship on the log odds scale, there will also be a relationship on the odds scale and on the probability scale. So we can still use, as you'll see below, we can still use this table of parameter estimates and their p-values to talk about whether there's a significant relationship or not. But beyond that, we're not going to interpret these values so much on the log odds scale. But now let's think about the odds scale. So if we want to think about the intercept, remember that our estimated intercept was 3.1186, which I'll just round to 3.12 here. And if we want to convert to the odds scale, we can take e to the beta 0 hat, which is what I'm doing here, e to the 3.12, which is 22.646. So the interpretation on the odds model scale is to say, we could say when age equals 0, the odds that, oh, I'm having a hard time spelling today, even words like that. The odds that y equals 1 is 22.65. Even better, we could put this in the context of the problem. Okay, so we could say when age is equal to 0, the odds that a person gets at least 7 hours of sleep on average is 22.65. So you could argue age equals 0. We don't have anything close to age equals 0 in our data set. Age 14 is the smallest age we have. So it's extrapolation, indeed. But at the same time, this also makes sense, right? When somebody, for newborn babies, they generally get at least 7 hours of sleep. Fingers crossed, right? And so the odds are very high that a baby will get at least 7 hours of sleep. Now if we want to think about the slope, how do we interpret the slope on the odds scale? E to the beta 1 hat is equal to exponential negative 0.15, which is what we saw up here in the table, which is 0.86. So we can interpret this on the odds scale as when age increases by 1 year, so for each 1 year age, the odds of getting at least 7 hours of sleep decreases by a factor of 0.86. So remember what we showed on the previous page, that on the odds ratio is really a multiplicative change with x. So when x increases by 1 year, the odds of getting at least 7 hours of sleep decreases by a factor of 0.86. I just want to note here that so it decreases by a factor of 0.86. We can also interpret, and this is sometimes more useful, odds ratio as relative change. So we can think of it as e to the beta 1 hat minus 1 times 100%. Is what I mean by relative change. So the way you might interpret that would be, as age increases by 1 year, the odds of getting 7 hours, I'm going to abbreviate this because I'm at the bottom of my page here, decreases by, so if we want to, our e to the beta 1 hat is 0.86. So this is 0.86 minus 1 would be negative 14 times 100%. So negative 14%. So it decreases by 14%. So we can also think of the odds ratio in terms of relative change. The odds either decreases by a factor of 0.86, or you can also interpret it as a decrease of by 14%. So let's see what else we can do with this. Now let's interpret this on the probability model. So remember, probability, and I'll write this again, probability equals odds over 1 plus odds. Right? So the odds for the intercept, remember the odds were e to the 3.12. So the probability is going to be exponential 3.12 divided by 1 plus exponential 3.12, which you can multiply out to be 0.9577. So the interpretation on this scale is when age is equal to 0, the probability that a person will get at least 7 hours of sleep, according to our model here, is 95.77%. Okay, we can interpret this as a probability. And if we want to interpret the slope, remember that beta 1 hat is, so beta 1 hat, or I might also use B1, is about negative 0.15. So it's negative. So I would essentially just interpret this S curve. So if I want to interpret that number, it's much easier to think just as age increases, the probability of getting 7 hours of sleep, I'm going to shorthand this, decreases. But we can do more with the probability model. So this is sort of a maybe an unsatisfying interpretation of slope. I'm just interpreting the sign. But I can also plug in some values to get some specific predictions. So what's the probability, based on our model, what's the probability that a student who is 16-year-old will get at least 7 hours of sleep? So what's the probability of getting at least 7 hours of sleep given that x is equal to 16? Using my shorthand notation here. Remember that probability is e to the, or estimated probability in this case is e to the b0 plus b1 times 16. We can plug in 16 over 1 plus e to the b0 plus b1 16. We can plug in our estimates for B0, or our values for B0, which are the estimates for beta 0, and B1, which is the estimate for beta 1, times 16. All of that over 1 plus e to the B0 This is a minus sign in here. So I'm just plugging in my linear equation and exponentiating it. And if you calculate this, and be careful when you put this through your calculator, I would suggest actually calculating whatever the numerator is first, and then just plug that into your denominator. You will get 0.6726, or the probability is 67.62%. that a 16-year-old will get at least 7 hours of sleep. So how does the model, the model fitted value, which is 67.62, compare to the observed value, which is 0.68? If we look back, for 16-year-olds, our observed value was 0.68. So p hat for 16-year-olds based on our data was 0.68. So pretty close. Very close.